Okay, guys, question 5. It says that show that the electric field strength E and the potential V at the surface of a charged sphere of radius R related by E equals V over R. So we're trying to show this here. Obviously, the field strength E is 1 over 4 pi E naught Q over R squared. V is 1 over 4 pi E naught Q over R. And therefore V over R will be Q over R squared. That's just basically saying that. And therefore it just said, well, E equals this lot here, which is that, which is equal to this lot here, which is that, which is equal to that. It's probably a quicker way of doing it, but that's how I did it. Anyway, on with the show. Number 2. It wants us to, the dome of Van de Graaff generator has a radius of 2.0, and it says that the dry air ceases to be an insulator if the field strength gets to 3.3 kilovolts. So we now know what the maximum voltage the dome can take. Well, V is E times R. That's the maximum voltage dry air can withstand before it ionizes, and 0.2 is the radius of the dome. So it comes to 6.6 times 10 to the 5 volts. B, calculate the peak potential of the conductor. I'm not sure where you do this in the series. I can't remember the top of my head now. I assume you've done it, but maybe not. RMS, root mean square of a AC waveform, is the peak voltage divided by root 2, sorry. So it's 100 kilovolts, which is the RMS, times by root 2, gives you 141 kilovolts. B, part 2, calculate the minimum diameter of the sphere necessary to ensure the surrounding air does not conduct. Well, we set it up here, E equals V over R, so R equals V divided by E. We calculated the maximum voltage, the peak voltage, which is that, and the electric field strength when the air starts to ionize and conduct. That gives us 0.43 meters for the radius. Of course, it asks for the diameter, so we have to double it to give the diameter. Righty ho, question 6. Lots of stuff to do for question 6. It shows a small charged sphere carrying charge Q. The potential of the sphere is 8,000 volts. Copy figure 6. So that's basically do a diagram. That's that first bit there. Draw on your diagram at least 6 lines to show the direction of the electric field around the charged sphere. So, word to the wise, it's easier to draw 8 than it is to draw 6 because it's a cross and then it's another cross. So anyway, at least 6. I've done 8 in green. You want to show them all equidistant. You want to show them all radiating away from the, to be honest with you, I should have done them going just from the surface of my sphere. I've messed this up a bit. Anyway, there's no field strength inside the sphere. So I'll get rid of these. But you should just draw them going from the surface of the sphere. Then you want to do 2, draw on your diagram the equipotential lines for potentials of 4,000 and 2,000. Now, again, if you think about the potential, V equals Q over R, obviously times by 1 over 4 pi E naught. But the point is, if this distance here, this radius here, gives us a potential of 8,000, doubling the radius there, so we've got, this is now 2R to that point, will half the potential. And then from the centre of the sphere, obviously doubling it again will give us half again, 2,000. So from there to there gives us 8,000. If we double the radius, there you go, from there to there you get half the potential. And if you double it, if this is 2R and then altogether this is 4R, you halve it again. Part 3 wants to know what E naught is. Of course, it's the permittivity of free space. B shows you some plates with some plates with a charged sphere inside and a spring to support it. It wants to know why it's on a nylon thread. Of course, that's because it's an insulator, so it'll keep the charge on the sphere. Part B, calculate the extension of the spring when a sphere of mass 1.5 grams is suspended from it. Well, extension, Hooke's law, F equals K delta L, so delta L is F over K. The mass times by gravity divided by the spring constant, which they give you in the question somewhere, wherever they give it to you. trust me, they do. It's 0.18 newtons per kilogram, newtons per meter. So that gives you an extension of 0.08 meters. Okay, I can't see where they say, there it is there, 0.18. Okay, B part 2, so B part 3 asks for the magnitude of the electric field strength when the plates are switched on. We've got 30 millimeters between the two at 8,000 volts, so it's the V over D, and that gives us 2.66 times 10 to the minus 5 newtons per coulomb or volts per meter. 4. When the 8,000 volts are switched on, the sphere moves down a further 4.5 millimeters. Calculate the charge on the sphere. So first thing we've got to do is work out what the force on the sphere is. So F equals delta L times K. That's the extra that's moved down 4.5 millimeters times by K. That means the extra force applied to it was 8.1 times 10 to the minus 4 newtons. And then of course, well, force is E times by Q, and therefore Q is force divided by E. We know the force and we know the field strength, so we can say what the charge on the sphere is. That comes out to 3 times 10 to the minus 9 newtons per coulomb. Okay, that's question 6.